Hello everyone, here we'll be discussing about energy, and the first thing we need to discuss is what is called work. It's basically energy at motion or during motion basically. In fact, there's a type of kinetic energy, as we'll find out shortly after. But let me just say that work is the act of applying a force on an object over a given distance. So we have this equation very, very similar to Newton's equation, F equals ma. This is W equals Fd. And in fact, if you kind of consider the units here, the standard unit for force is going to be in newtons, and then for distance that would be in meters. So work is Newton meters, but much like how for newtons we define that in terms of the formula, we have a similar unit for work, and the work per unit we're going to be using is what is called joules. So joules is actually a pretty commonly used unit for energy. Yeah, that's kind of all I really want to say there. I guess one thing you could say is that notice the standard unit in imperial, so this is in metric, but imperial it would be foot-pounds, which also is pretty commonly used as well. And now this equation is from magnitude perspective, of course. We can discuss this as vector quantities as well. So in general, we basically have W as a vector equals force as a vector times the distance as a vector. And of course, normally we consider the net work, kind of like we consider the net force. So I'll subscript that accordingly. And notice if you consider, let's say, the x component of work, that would be equal to the x component of force times the x component of distance, which would be delta x. And similarly, you can discuss for y, it'd be times delta y. That's all I want to say there. Now, here we have an example. We're just going to kind of cut to the chase. So here we say that a man pulls a sled full of salmon. So I guess he's coming back from a successful fishing trip with total mass of 50 kilograms. So the load he's pulling, I have a picture here. The load he's pulling is 50 kilograms mass with an exerted force of 120 newtons. So he's pulling with 120 newtons of force at that particular angle. And notice in general, before we even begin, there's actually a few different forces acting on this sled. So there's the so-called normal force, which we call N. There is the weight, which is the force due to gravity, which we normally just call mg. Also note here, it's the magnitude will be negative. Well, the force is negative, but yeah, that's fine. And then here we have the resistant forces or friction forces, which we could call F sub k or something like that, but I'm not even going to label that. And then here we have the exerted force. So the net force here would just be this force minus all resistant forces. Okay. But we're going to assume that this total exerted force is the force accounting all of the friction. So, right. So now we're asked to find a few things. The rope required to pull horizontally, distance of 5 meters. So notice we have a distance, we have a force, so basically just multiply those. And then here we want the work required to pull at an angle of 30 degrees. So we'll have to find the x component of the force, so Fx in this case. And then we have the distance also, so multiplying those would be okay. And then finally C asks, if after 12.4 meters, the man stops pulling and the ice surface has a friction force of 45 newtons, then it will stop the sled after 18.2 meters. When I say after 18.2, notice it started after 12.4. So 12.4 meters from the initial starting point, he stops, and then where he stops pulling, and then where the sled stops due to the ice friction will be 18.2 meters from the initial point. So delta x in this case will just be the difference between those. And here we want to find the work done by friction in order to stop the sled. So I'm going to erase a lot of this and then we'll rewrite the questions and we'll proceed like that. Alright, so I've erased a lot of things. I've rewritten each part with a few things added, and then I'll kind of real quickly want to label this now. So this is F sub k. Remember that is the frictional kinetic force or kinetic friction force. And for whatever reason we use lowercase f in that case. And the k stands for, again, kinetic. It's negative because it's going against our pull, but we're assuming this pull is not considering that force, actually. So otherwise we would have to subtract that horizontal component of our force, of our pull, minus this. So this is considering friction already, actually, but then when we let go, then we consider the friction alone. So what we're going to do for these problems is that for A, our horizontal pull is Fx itself, so that's where the angle is 0 basically, and the distance we're pulling delta x is going to be 5 meters. And here the work, since it's purely horizontal, well, in fact, since the sled is being pulled horizontally, the only real work, the net work, will actually be the horizontal work. So I'm going to describe that here. And the reason being is because, well, work is, let me see how I can describe it. Well, work is force times distance, right? And the reason why there's no vertical force in this case, or vertical work in this case, is because there is no vertical net force. If there was, then the sled would move up or down. Since that doesn't happen, then the vertical component of the net force is 0, so then the vertical component of the net work would be 0 times that mass, times its mass, not times its mass, I'm sorry, times the distance, since work is a multiple of force. So in that case, the vertical component of work is 0, meaning that the net work in this case is just going to be the horizontal component alone. So W in this case is equal to Wx. And I guess you can write W net, but that's fine. I'm just going to write W for W net, just to not have too many labelings. Anyways, what we're expecting now, I think, is just finally the equation, and then multiplying these things together. So we go 120 times 5, and that's of course going to be 600. And the unit, of course, is Newton meters, which we know now is joules, capital J, and there we go. Now here, well, we have to now consider essentially the horizontal force, because we have this angle. The horizontal component of this force, vector force, would be F times cosine of the angle. So that's of course 120 times cosine of 30 degrees. So we'll have to use our calculators to approximate this, and then multiply that result by 5 meters, which is delta x. So this is going to be, again, W is still Wx, which is Fx delta x. For the same reason W was equal to Wx from the first one, there's no vertical motion at all. There's only horizontal motion. So the net work is purely horizontal in that case. So now again, this is going to be whatever Fx is times whatever delta x is. Delta x is just 5. And now let's approximate Fx. Right, so now using my calculator, I got, well, 103.9 for the horizontal component of force. Multiplying these now will give me about 520. It's like 519.6, but let's round it up to 520 newtons for a nice clean whole number solution. And now let's move on to the next problem. Now here, Fk is negative, which makes sense because, again, it's a negative vector in the sense that it's going in the opposite way that we're going. It's going against our pull because friction tries to slow something down. So that makes sense. It's going against our initial pull. Of course, we let go, the force is going to be strong enough to eventually stop the sled. So this is mainly just going to be Fk times delta x. But notice since F sub k is negative, the work would be negative. Negative work just means that we're stopping something from happening. It's going in the opposite direction, basically. So work can be negative. Okay. And in fact, the way it could be kind of understood is that work is setting something in motion, and a negative work would be trying to stop that thing. So imagine a bunch of people trying to stop a car from rolling down a hill or something like that. That would be negative work because they're going against the object that's moving. Okay. So this is, of course, negative 45 times delta x. Delta x I kind of did for us already. That's the final minus initial x values, which was just 18.2 minus 12.4 meters, which is 5.8. Now, if we multiply these numbers together, we will get about negative 261. Yeah, that works. And that's, of course, in joules. Okay, great. So that's all I want to discuss as far as work goes, but we're still going to talk a little bit about work right now, but now we're going to see something a little different, and we'll actually see a few new things come into play now. All right, so the next that we need to talk about is something called kinetic energy. And kinetic energy basically falls out of a particular case of work where we consider horizontal only. By the way, it's a little technical, but I kind of misspoke earlier when I wrote an arrow on top of work. Work technically is actually a scalar quantity, not a vector quantity. But still, to consider components of vectors for at least the force and not velocity, or force and displacement, that would help. But just keep in mind that work is just a number only. It has no direction, it's purely magnitude. Okay. So with that being said here, let's see if we can, and for that reason, the subscript on W is never really a thing. So when I wrote WX, that's kind of a little misleading as well. Really, it's just W net. But again, that's a little technical. So what we're going to do essentially here is we're going to expand force. Remember, force is mass times acceleration. And then notice we have A delta X, and that should remind us from kinematic equations. There's actually a very particular kinematic equation that comes to mind, and that's V squared is equal to, well, actually I think it was V squared minus, okay, so it was V squared equals V naught squared plus 2A delta X. There we go. Sorry for the slight pause there, just trying to recall what that was. This is the fourth kinematic equation. And you can solve for delta X. Notice all that entails is just subtracting these velocities like this, and then dividing by that 2 in front of the A delta X. Perfect. So now with that in mind, we have this, of course. And notice if you, well, I guess multiply things correctly, you can actually get a nice difference of two terms, which work is equal to. So now we'll say the net work is equal to, so I'm going to pull this 2 out as a 1/2 and then distribute the m in. So basically this is going to be 1/2 m v squared, which is v final squared really. So I'm just kind of changing the notation a little bit. Minus 1/2 the mass times v initial, so I'll call it vi for v initial instead of v naught, just in the context of this. And now I'm going to tell you that we are going to basically define, now kind of off to the side, from this we're going to define each of these terms as what is called kinetic energy. So capital K and capital E, and that is an energy measured in joules, just like work is an energy measured in joules. And that's just going to be one of these terms. It's going to be namely 1/2 mv squared. So this is our definition, so I'll write a 3-bar here for definition. Okay, so with that being said, we can actually write this as net work is equal to, well, Ke final minus Ke initial. In other words, we have final minus initial quantity, and what do we call final minus initial? We always call a final quantity minus initial quantity delta that quantity. So we basically get this nice relationship here, that the net work is actually equal to the change in kinetic energy. Awesome. Now what kinetic energy really means is energy, energy while an object is in motion basically. As we'll see after this, we'll discuss, eventually, we'll discuss potential energy, which is an energy that an object has while it is not in motion, that is kind of building up and waiting to be set in motion and then converting that now into kinetic energy. So kinetic energy is while it's happening, basically. So in this example, we have a 1,000 kilogram car and it brakes with a force of 8,000 newtons. So basically when it applies the brakes, it exerts a frictional force on the wheels, you can think of it like that, 8,000 newtons. If the car was going 35 meters per second before applying brakes, and comes to a halt, we want to find the following. We want to find A, the minimum distance a car must travel to avoid a rear ending. So imagine it's, in front of or in back of a car, so it has a car in front of it that's at a dead stop, and it sees the car stop, so it applies the brakes and hopefully prevents that accident. What is the minimum distance that the car must be away from the car in front that's at a stop in order to come to a stop and prevent the accident? That's what A is asking. Now B is asking if the car in front at a dead stop is 30 meters in front, find the velocity of the collision. So this kind of spoils A a little bit because it tells us that the minimum distance must be bigger than 30, otherwise it wouldn't say that a collision would happen at 30 meters regardless of the brakes being applied with this much force. So anyways, much like we've been doing, I'm going to erase a few things here. I'm going to rewrite what we need and what we have for A, B. And I'll leave this image here, of course. And notice we have our initial velocity, we have our frictional force due to the brakes, and the distance delta x between the two cars. So now let's get to it. Alright, so I've erased a bunch of things, and we're going to actually start here with A. And here we know the car stops, so that means the final velocity is going to be 0 meters per second. And we're going to actually consider the work that the brakes do on the car. So really this is, our net work is going to be, in this case, it's going to be the work due to friction, so we can call it W sub fric, I guess, for friction. And now notice that work is what? Work is force times distance. So we have the force, actually, it's Fk in this case, and we have the distance, that's just delta x. But that's what we're trying to find. We're trying to find the minimum distance that we need. So this delta x is actually what we want to find. Delta x is our want to find, let me just say, if we remember that acronym. And now notice that this is just negative 8,000 delta x. Now again, why it's negative is of course because the friction force is going against our initial velocity, so that it's slowing us down. And yeah, okay, so I think we're okay here. Now what we want to use is the fact that work is equal to the change in kinetic energy. So namely our work, our frictional work, is equal to the change in kinetic energy, which we know is just, well, 1/2 mv final, mv squared final, minus 1/2 mv initial squared. Good. So now we know our final force is 0, so this is just going to go to 0 because the final force is 0. And we know our initial velocity, and we know our our final velocity is 0. Our initial velocity we know is 35 meters per second. And I think we're good to go. So we get negative 1/2 times our mass, which is 1,000, times our velocity squared, so it's 35 squared. And you can use your calculator here. And I actually got negative 6,12500. Now here, again, this is equal to what? This is equal to, on the extreme left side, we have the friction work, which we found on top here is negative 8,000. So it's negative 8,000 newtons times delta x. So negative 8,000 delta x is equal to this, so now all we need to do is divide by negative 8,000. And now we finally get that our delta x value is just this divided by this, and I got about 76.6 meters. Awesome. So I hope that was okay to follow. So basically I'm using that work is equal to the changing kinetic energy. The final kinetic energy is 0. The initial kinetic energy we know based on information we have from part A. And the work we actually found separately first. That was the given negative force times our delta x value, which is what we want to find. And then we can just divide after calculating the right hand side. And there we go. So now I'm going to erase and do B. So in this case for part B, it's actually quite the same, only we have different information. So some roles are reversed. So here instead of stopping, we actually don't stop. Well, I could kind of stop. The collision basically allows us to stop. But we're traveling a given distance of 30 meters, and we want to find the final velocity. So in the previous problem, part A, final velocity was given to be 0, and we needed to find delta x using the given stuff up here. So now we're going to again say that the net work, which is the work due to friction, is the change in kinetic energy, which is 1/2 mf squared, mvf squared, minus 1/2 mvi squared. Now in this case, we don't know what mvf is. Notice since mass is 1,000, this is just going to be half of that, which is 500. That's kind of nice, we can do that. And vi we know, in fact we calculated this earlier and we got what, 6,12500 I think. 1/2 times 1,000 times 35 squared, and yeah, that's what I got. Good, just kind of recalling that. And here, what is the work due to friction? We actually found that also. Well, kind of. We didn't actually find that because now we have a different delta x. So this is just Fk times delta x. So work is Fk times delta x. So this is really just negative 8,000 times 30. All right, so now, well, we're just going to combine things and solve. So notice these multiply to negative 24 with 4 zeros. That's a 0. This stays the same, so it's 500 VF squared minus 6125000, or just 2 zeros. And in fact, speaking of 2 zeros, they all have 2 zeros. So if you divide by 100, that cancels out these 2 zeros for each of them. And in fact, you can even go a little further and divide by 5. So I'm going to do that actually. So I'm going to just write here, divide through by 5. If you divide this by 5, it should be negative 480. If you divide that by 5, the 5's gone. If you divide this by 5, I believe you get 1225, looks like. And then adding this to the other side, gives you, I believe, I got 745. And then finally, if you square root both sides to get VF by itself, of course it's going to be the positive value. It's going to be approximately, I'm getting 27.3 meters per second. Awesome. Good. So I hope the way I solved this didn't confuse us too much. I just simplified as we went along. I noticed there were some things each term had in common. So I just divided accordingly to get more simple values. All right, so that's, I think, all I wanted to say there. Now we're going to move on to what I said earlier, potential energy. In fact, we're going to discuss something called the Work-Energy Theorem, or I believe that's what it's called. But it'll discuss potential energy as well as a few other more general things. So let's take a look at that right now. Right, so a few things. The Work-Energy Theorem actually, technically, is what we kind of saw already, and that's that net work is equal to change in kinetic energy. So that technically is called the Work-Energy Theorem. But there's a little more we can say. We can actually expand this out into something kind of new. We can say that net work is actually the sum of two different works in reality, the so-called non-conservative work and conservative work. So the NC here stands for non-conservative, whereas the C stands for just conservative forces, or conservative work. And of course I say forces because work is force times the distance, so conservative and non-conservative work have to do with conservative and non-conservative forces. Okay. Now exactly what that means, what non-conservative and conservative forces mean, or work means, without explaining in too much detail, so the conversation doesn't get too complicated, non-conservative basically are random, different disperses of energy, kind of just randomly in nature, I guess you can say. I don't want to say like wind resistance and stuff like that, but some things that bodies in nature just randomly disperse, which I know sounds a little weird, but that's what non-conservative forces are. Conservative forces are things that kind of go against you, and that's the best way of describing it. So friction is an example, but the best example of conservative forces is gravity. So there's actually the force due to gravity is a conservative force. So the work due to gravity, gravitational work, is a conservative work. Now, we're going to be talking here about gravitational potential energy, and potential energy is, well, gravitational potential energy anyways. We'll use PE for potential energy, kind of like we use KE for kinetic energy. And I described already that potential energy is the energy an object contains before it is acted on by any other force, by any outside force, you can say. Any external force, I guess, is the best terminology. So PE sub g, the gravitational potential force, is just mg times y, where y is the vertical distance that is traveling, and mg is the force. Well, the force due to gravity, so it's weight basically. Okay. Now, the thing I want to say about this is that force due to gravity, the weight is usually negative if you think about it because it's pointing downward. And for that reason, consequence of this is that gravitational work is, well, it's the change in potential gravitational energy as it turns out. And I'll describe that a little bit here because notice, work is force times distance, so it's going to be the force of gravity multiplied by the distance, which was delta y in this case. So notice here, if you expand this out, since gravity, well, force due to gravity, I should say, is negative mg, because it's downward again, and this is, of course, yF minus yi. This is very similar to what we saw for net work with horizontal motion, where we expanded it out and we got a formula for kinetic energy. If you expand this out, that's when you get the potential energy. So this is negative mg yF, and then I guess it would be positive mg yi, but I'm going to actually leave the negative on the outside and distribute the mg only, so that we get this. And you'll see why I'm going to do that in a second. And it's because I'm going to just call this negative, and notice this is PGI, or I guess PGIF, so the final gravitational potential energy, and this is the initial one. So really what we can say is that this is negative the change in gravitational potential energy. Nice. And with this in mind, since conservative forces is a gravitational energy, what we can say is if we are in a scenario where the only conservative force in mind is the gravitational, if the only conservative work in mind is a gravitational work, then this version of the work-energy theorem actually becomes the following. So if this is the case, then our work-energy theorem, which I guess you could call WET for short, like as an acronym, it becomes what? It becomes non-conservative work plus conservative work, which is just WG, is equal to delta KE. But notice this is negative PEG, and in fact if you subtract this to the other side, like that, then negative WG is just positive delta PEG now. So now we get non-conservative work is actually equal to the sum of the change in kinetic energy and the change in potential gravitational energy in this case. Which is pretty nice to see that. In fact, we'll see different versions of the work-energy theorem that expand to something very similar to this, where non-conservative forces are basically the sum of these two change in energies, change in kinetic plus change in potential. I don't really have room for this, so I'm going to erase and rewrite this above, and I'm going to rewrite this in a different way. And the form that we'll write it in is known as the conservation of mechanical energy. Right, so I've erased all that and I've rewritten this up here. So basically the work-energy theorem implies or gives this equation on conservative work is equal to the sum of change in kinetic energy and potential gravitational energy, or gravitational potential energy, however you want to say it. But now I'm going to kind of consider something. Now, this is called the conservation of mechanical energy. So let me just say that the conservation of mechanical energy basically only applies in the scenario where we have no non-conservative work. So we're letting W and C equal 0. And in fact, I had mentioned to you earlier, well, when I was trying to describe non-conservative work, it was a little difficult to describe, and that's because normally we don't even consider it for these scenarios. It's too technical, and basically you'd be only considering it if you're being super realistic about things and kind of studying specific instances in nature. But for right now, well, for this class anyways, we're going to consider that the non-conservative work is 0, so that now we can discuss the conservation of mechanical energy. And notice when that's 0, we get this. And I'm going to expand this out a little bit. So it's going to be KEF minus KEI plus PGF minus PGI, just like that. And if we move things around, actually notice the negatives here are the initials. So if you add the initials to the other side, you get the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final gravitational potential energy. And this right here is the conservation of mechanical energy. It's the principle of conservation of mechanical energy. And you can even expand this a little further, keeping in mind that KE is equal to 1/2 mv squared, and PEG is equal to mgy. So I'm going to do that. It's going to be a lot of writing, but it's not too bad. So it's 1/2 mvi squared plus mgyi equals 1/2 mvf squared plus mgyf. Beautiful. So this is another version of the conservation of mechanical energy. All right. So now we're going to take a look at a particular example involving this. All right, so for this example, we have a diver jumping from a board that's 10 meters above water, and we're asked to find the velocity after 5 meters and then the velocity when hitting the water. Now, to be honest, this can actually be done using one-dimensional kinematic equations, but it's nice to see that the conservation of mechanical energy actually applies here. So I'm going to consider that actually for both of these. So let me just say that, well, KEI plus PGI is equal to the finals, kind of like we saw. And right. And now what I want to do is actually I'm going to expand this out a bit, and then we'll kind of see what's applicable when, and then we'll actually jump into each problem. So here, notice this is again 1/2 mvf squared plus, this is mgyi, not f, this is I squared, there we go. This is 1/2 mvf squared, there we go, good. And this is mgyf. And I notice they all have m in common. So we weren't given the mass of the diver, it doesn't actually matter as it turns out. So we cancel m out right away. We can do that. And does it say the initial velocity? Doesn't say the initial velocity. So we're assuming that the diver's just, well, it says jumps from a board, but I guess maybe a better phrase is saying that the diver drops from the board. There's no initial velocity, so it's just, maybe it's better to say drop. I'm kind of changing the wording a little bit. There's probably a better phrase, but we're assuming that the initial velocity is 0. So in other words, since the initial velocity is 0, in fact, let me write that here. So assume initial velocity is 0 meters per second. So with that being said, well, VI goes to 0. So that actually goes to 0 in this case. So this first term is 0. And our final height is 10, so we know that. Our final velocity we're trying to find for each of these. And we have, yeah, so I think we're good to go. So this equation basically becomes GYI is equal to 1/2 VF squared plus GYF. And there is a way to move things around to actually get the appropriate kinematic equation we would have used otherwise, but that's okay. So now, well, I guess in particular we know that YF is 10, so that kind of changes things here a little bit. In fact, should I write that? I guess maybe might as well write that before we jump into things. So gravity, of course, is 9.81. I'll just write 9.8, just to not write too much. And then since YF is 10, no, not YF isn't 10, I'm sorry, YI is 10. So YF is different depending on the problem, but YI is certainly 10. So notice since YI is 10, because it's our initial height, then we have 10 times 9.8, which we're going to just call 98, like that. And we're trying to find our final velocity given these, given these final heights or final distances. So now for A, it's given that we're trying to find it after 5 meters. So the diver's velocity after 5 meters would be YF being equal to 5. So in that case, we can actually solve for VF. So we get 98 minus 9.8 times 5, which is just basically half of 98, so that ends up being 49. So I'm subtracting that to the other side to get 1/2 VF squared. I notice these two subtract to just be 49. We can multiply both sides by 2 because of this 1/2 here. So we get 98 anyways, which is kind of funny. So if 98 is equal to VF, notice 98 is pretty close to 10 to 100, which is 10 squared. So VF will be approximately 10 meters per second in that case. I'm not really doing too much calculator work here, but it's nice to see that we can indeed do this. So for B now, in this case, we're actually letting the final height be 0, because since the diver's hitting the water, then we'll be 0 meters above the water, basically. So in that case, that term goes to 0, so we just get 98 is equal to 1/2 VF squared plus 0, I guess, so don't even write it in my opinion. Multiplying both sides by 2, we get 196 is equal to Vf squared. So that means Vf is the square root of 196, which is about 14 something, and I'm getting, let's just round to 14. So I'm getting about 14 meters per second. Okay, good. So that was a nice application of the conservation of mechanical energy. The only issue, I think, is that really it just boils down to a kinematic equation. But it's a kind of nice generalization, but it's very specific in the sense that since it's gravitational potential energy, it can only be used for vertical motion problems. So I mentioned that we weren't going to talk too much about non-conservative work, but in some instances there's actually a way to solve for it, assuming that it's non-zero, and given that you have basically the left-hand side of the Work-Energy Theorem, well, not left-hand side, but given that you have conservative work handled and you have kinetic energy, then you can actually do so. So we're going to see an example of that right now before moving forward. Right, so now for this example, we have a 60 kilogram woman sliding down a water slide, and of course starting from no initial velocity. And the water slide is 21.9 meters above the ground, which is actually quite high. And we're asked to find these two things. So speed at the bottom of the slide assuming no friction, and work done on woman by friction if the final velocity is 18 meters per second. So kind of opposite things. Here we're assuming no friction, find velocity. Here we're assuming velocity. Well, for given velocity, we're asked to find friction. Now, something I want to say that, again, may have been a little misleading based on a discussion on non-conservative forces. I may have said that, well, I don't think I said the non-conservative forces are not friction, but I didn't give that as an example. And I think I may have said something that may have made you believe otherwise. But as it turns out, the best example of non-conservative forces, which by the way are kind of random in nature, is friction. So friction is a good example of a non-conservative force, where gravitational potential energy is a good example of a conservative force. Okay, good. So now let us remind us of, well, basically one of the results of the Work-Energy Theorem that's kind of like conservation of energy, but here we're not assuming W and C is 0. Now for A, we are assuming it's 0 though, because if we're considering this to be our friction, so to speak, then, well, then that's 0. So in fact, let me write that here. So the equation we'll be using is this. 0 is equal to delta KE plus delta PEG. And I'm going to actually expand this out kind of in general, and then see if we can solve what we want and apply what we have given. So notice that delta KE again is 1/2 mvf squared minus mvi squared. Okay, and our initial velocity here is 0, so we don't really care about that. This is equal to 0, plus our potential energy, the change in potential energy. And let's see, the change in potential energy here is going to be, well, that's mgi, or mgyf, sorry, minus mgyi. There we go. Now let's see, we want to find the speed at the bottom of the slide, so that means our final height above the water is 0, because we're hitting the water level here. And here I didn't actually draw an image for us, but if you want an image, basically slides like this, practically vertical, and you have a woman sliding down like that. We want to find her velocity here. But we're only considering the vertical motion, not the horizontal motion in this case. Okay, so the final height once she enters the water is 0. So really we just have this. And do we know VF? We don't know VF, we're asked to find that speed. So we'll find that. We know M and we know G and we know her initial height, that's this. And in fact, what's kind of nice here is notice that this equation really becomes the following. Let me write in this space we have 1/2 mgvf squared, 1/2 mvf squared minus mgyi. Now what's so great about this is that they both have m in common. So in fact we can divide through by mass, and notice that mass doesn't actually matter for this particular problem. Perfect. And we want to find VF, so I'm going to actually solve for that in general, well, before applying numbers anyways. So I'm going to add GYI to the other side. So we get GYI is equal to 1/2 VF squared So then multiplying both sides by 2, which I'll just do here like this, and then square rooting, we'll cancel the square. So we get the VF is approximately whatever the square root of this is. And in fact, let's plug in now. So it's equal to the square root of 2 times gravity times yi. Now gravity will take to be 9.8. So if you double that, you get about 19.6. And that, of course, is multiplied by the height, which is 21.9. So all we need to do is multiply these and take the square root, and I'll do that right now. All right, so I got 20.7 actually. And since this is a final velocity, it's going to be 20.7 meters per second, of course. Beautiful. So now this problem is a little different because we're asked to find the work done by friction. So here, we assumed that there was no friction. So that means W and C was equal to 0 because the non-conservative force of friction is 0 in that case. Here, it's not. So we're basically asked to find W and C. So we're considering the equation again, W and C is equal to this. Now what's really nice is that we kind of have the same thing going on here. In fact, the exact same thing. In other words, her initial velocity is still 0, her final height is still 0. So in fact, really we get this same equation we had here, only we can't divide through by m yet because instead of 0, we'll have W and C. So this equation boils down to W and C equals 1/2 mvf squared minus mgyi. Yeah. Okay. And again, we can't divide through by mass and just ignore it because we have this quantity now. But now we know what VF is. In this case, VF is given to be 18, and yi, of course, is 21.9. So really all we have to do is just plug in things into the right. So we have 1/2 times m. And notice since m is 60, 1/2 m is going to be 30. VF is going to be 18, so it's 18 squared. Minus m is 60 times gravity. So maybe I can, well that's fine, I'll just leave it like that. So 60 times gravity, let's call it 9.8, times our yi, which is 21.9. And now we'll just use our calculator to evaluate this, and that'll be our non-conservative work, which we know really is just our frictional work, or work due to friction. Okay, so let's see what that gives us. All right, so here I got about negative 3157. It was 0.2, but I'll just round to the nearest whole number. And that's of course going to be in joules because, well, work is in joules. Also, if you follow the units, it'll amount to joules anyways. And yeah, so now we're going to move on and talk about a different type of potential energy finally. And so now the next topic here can be a little lengthy to be honest, but I'm not going to talk about it in super detail, too much detail rather. But here we have what is called spring potential energy, where we start to consider springs and basically the act of pushing an object on a spring and compressing the spring, and then letting go, the spring does work. So this is a nice image here. So we have this object that has mass, and we're going to push it towards the spring, and then once it's kind of pushed so that the spring is compressed, then there is a potential energy that is locked due to the spring. The more we push it in towards the spring and the more we compress the spring, the more energy, more potential energy is at hand in that case. And then once you let go, then the object is pushed in the opposite direction basically. Now we have this property here called Hooke's law, and Hooke's law says the force due to spring is equal to negative kx. The negative is basically telling you that the force that the spring pushes on an object is in the opposite direction, hence the negative. The k is what is called the spring constant, and that varies from spring to spring. Some springs have a larger spring constant than others. Of course, some springs are thick, other ones are kind of thin and long, for instance. In fact, this idea goes beyond springs. If you kind of think of bungee cords, they have elasticity. Elasticity has a spring constant that can be measured in the same unit. And by the way, the unit for the spring constant is going to be in newtons per meter. So what this says is that for every meter, there's a certain amount of newtons of force that can be applied in the opposite direction, which makes sense. So x is going to be our distance. So let me say here, this is spring constant. and this is distance from equilibrium point. So I'll just write EP for equilibrium point. Now the equilibrium point is where the spring is at equilibrium, where it's not compressed or stretched. You can stretch a spring, by the way, and basically in that case the x value will be in the opposite direction. In fact, very often the way this is denoted, we often think of x values to be negative when you push it in. So when you let go, the resulting force will be positive now. But if you pull it, then you have a positive x value, in which case when you let go, you'll now have a negative spring force. Okay. Now, the spring constant is always positive, and it's universal for each spring. This should kind of remind you of mass, maybe. Mass is, well, always positive, and it's universal for each object, kind of like how spring constant is universal for each spring. Okay, good. So with that being said, we can kind of mimic, so to speak, kinetic energy, the equation for kinetic energy, with the, this equation for potential energy from spring. So spring potential energy is 1/2 kx squared, kind of like how kinetic energy is 1/2 mv squared. So k and m are kind of playing the same role, and x and v are kind of playing the same role in this case. And notice x may be negative, but when you square it, doesn't matter anyways. So for that reason, potential energy for a spring at a given point will always be positive. Okay, good. So now, as a consequence from the work-energy theorem, potential energy, any type of potential energy, is a conservative force. So that actually gets expanded beyond potential energy for gravity, gravitational potential energy. In other words, we now get a new term here in this expansion. Now, if there is no spring in the problem, then of course this is 0, and we just basically have the problems we had before. And vice versa, if there's no vertical movement, then gravity isn't applied at all, or there's no y's, y and yf are the same, I guess you can think of it like that. And then this is no longer applicable. And then if you have neither of them, then you only have this. Okay. So now we're going to see an example involving this. In fact, this will be the only example we'll talk about as far as spring potential energy. And then finally, to finish the video, we'll talk about one last idea, but I don't even think we're going to talk about it in that much detail. We may do one example, but let's see the example for this and see what that entails. All right, so here for this example, we're given a 50 kilogram circus acrobat who drops from a height of 2 meters straight down onto a springboard with a spring constant of 8,000 newtons per meter. And by what maximum distance is the spring compressed? So I've drawn an image here where we have this acrobat dropping down toward this springboard, and then when she lands, it compresses a bit. So by what distance is the spring compressed? So what's this distance here? This is kind of before and after. Well, what we're going to do is we're going to, of course, assume that there's no friction in this case because it's not even brought up in the question. So we're essentially going to assume that non-conservative forces are 0. So remember that non-conservative work is equal to the change in kinetic energy plus change in potential energy plus change in, spring potential energy. This should have been gravitational potential energy. All right, so now applying this when W and C is 0, in fact, I guess what you can do is you can rearrange things kind of like we saw with the conservation of mechanical energy. So if you like, I'll actually do that if that's okay. So I'm going to write initial equals final. So I got KE initial plus PEG initial plus PES final. Initial, these are all initial, equal the final ones. So KE final, PEG final, a lot of subscripts, plus PE final. And that's, of course, by just writing these as final minus initial. And since all the initials are negative, we'll add them to the other side when W and C is 0. That's kind of what we're assuming here, that W and C is 0. And a lot of nice things happen. In fact, I'll kind of try to show that right now. So the first nice thing that happens is that the initial spring potential energy is 0 because it's at equilibrium at this point. X is 0, it's not compressed basically. So this guy is 0 for the initial spring potential energy. And the final kinetic energies are both going to be 0 here. And the reason being is because remember, kinetic energy is 1/2 mass times velocity. So there's 1/2 is non-zero, mass of the acrobat's non-zero, but the velocity, final velocity is 0 because she stops. So that's 0. Potential gravitational energy is also 0 because this is mgyf, and yf, her final height above the ground or above the board anyways, is 0. Good. All right, so I'm going to expand this out a little bit. Notice kinetic energy is 1/2 mvi squared. Potential energy is, well, mgyi, and this should be psf. There we go. And that's 1/2 kxf squared. So we kind of have to be a little careful here because there's some ambiguity. In fact, I'm glad I had this picture here. So notice there's actually these two vertical distances. This vertical distance, let me show in red, is x. The amount that's being compressed. So that's x. Okay? There's this distance that she drops, which is given to be 2 meters. She's 2 meters above the floorboard, but when she lands, she actually lands a little lower because the floorboard compresses. So in total, this distance here, 2 plus x, will actually be her, her initial height. So the total delta x really is going to be that. So her initial height above where she lands, so yi, is 2 plus x. So keep that in mind. So in fact, I guess we can pull out m here if we want to solve for fx and then plug in, which I like to do. So I think we'll do that actually. So let me factor out m, and then we have vi squared. By the way, her initial velocity is 0 because she's just dropping. So this is also one that actually goes to 0, which is nice. She starts with no initial velocity. So in reality, we don't have to pull out anything, but we can actually replace yi with just 2 plus x now, which I guess is xf technically, equals 1/2 k xf squared. So I guess we can solve again in general, but you know what, it kind of seems like this is going to be a quadratic equation, so we need quadratic formula maybe. In fact, I think what I'm going to do here is I'm going to actually write in the numbers instead and then use quadratic formula. So let's see if we can do that. So m is 50, g is 9.8. Let's see, 9.8 times 10 is 98, and then 98 times 5 is going to be half of it. So it's going to be 490, sorry. 2 plus that. 1/2 k is 8,000, so it's going to be 4,000. We're trying to find this. So you know, actually it's a little helpful if we just call xf equal to x. That way we don't have to write too many subscripts. I think we're actually going to be really, really good. Because if we move things around, I'm going to subtract those to that side, but I'll write it on this side if that's okay. So we got 4,000x squared minus 490x minus 980 equals 0. Now, in fact, we can divide by 10, let's say. If we divide through by 10, then this becomes 400, this becomes 49, and finally that becomes 98. And that's all we can divide. You can divide by 400 if you want, but I'm not going to do that. You'll get weird decimals in that case. So now I'm just going to apply quadratic formula, and let's see what we get. So by quadratic formula, we get x is equal to, so negative b is negative 49 in this case, so it's positive 49, plus or minus the square root of negative 49 squared, which is just the same as 49 squared, minus 4 times a, which is 400, times c, which is negative 98. But notice, if I wrote negative 98 here, we'd have 2 negatives, so that just becomes positive, really. And then all divided by 2 times 400, which is 800. So now I'm just going to do some number crunching on my calculator, and I think we're only going to need the positive one because I think the negative one, well, I guess actually it kind of depends, doesn't it? Let's see what we get for both of them, and then I'll kind of reason it out from there. All right, so as it turns out, we're going to take the positive one, and the reason being is because if x was negative, notice the way we're using x here it's added to 2 to make a longer height. So even though the spring is compressed, and I mentioned earlier that when you compress a spring, at least with that orientation I gave you earlier, it's a negative x value. But in this case, we're seeing it as only the positive value there. And of course, again, if it was negative, then it would be 2 minus x instead of 2 plus x. So for that reason, we're going to deal with the positive one only, and we get actually about 0.56 meters. Awesome. And now finally, we're going to move to the last concept of this section on energy, which is power. It's going to be a really quick discussion though, so let's see that right now. So the last thing we want to talk about now is power. And let me just say that power is basically just, pretty short, the rate of change of work. So it's how fast work is changing. So power, average power, so P bar, is work over change in time. Now notice, since work is, let's call it a F times delta X, this is pretty interesting because notice delta X over delta T is just velocity. So you can think of this as force times average velocity. And for instantaneous power, we just say P is equal to force times velocity. Fantastic. Now the unit of power, by the way, is in watts. And 1 watt, by the way, so let me say W, but of course watt is spelled like this, W-A-T-T, just to show you. And 1 watt is, well, if you look at these units here, it's going to be equal to, so we write a 3 bar for definition. So a definition is 1 Newton times meters per second, because of course velocity is meters per second. And in fact, notice, since Newton meter is joules, this really is the same as 1 joule per second, which makes sense because it's how fast work is changing. In fact, basically you can think of this as consumption by, let's say, an electrical item, like let's say a light bulb, for instance. Watt is basically how many joules it eats per second. Nice. Okay, so now there's this kind of standard in imperial that we often use a lot in the US, which is horsepower. So horsepower is 550 feet-pounds per second. And that actually approximates to about 746 watts. In fact, very often people think of this as, at least I think of it anyways, as 1 horsepower is, you can think of this as a 0.746 kilowatts. And notice that's pretty close to 0.75. So very often I think 1 horsepower is equal to 3/4 of a kilowatt. I think that's a nice way to think of this conversion. It's pretty nice. Good. So now for this example, we have a 1,000 kilogram elevator that has a max load of 800 kilograms. Okay. And forces due to friction are constant at 4,000 newtons. And we're asked what minimum power in horsepower and in kilowatts, so the conversion's nice here, so that's not too bad, must the motor deliver to lift the full load at a constant velocity, let's just say velocity, of 3 meters per second. So let's see, we want to find power in this case, but we're given a few things. Now, in fact, if you look here, we're given some forces. In fact, really we're only given 1 force, but we also have this mass, basically. And notice that mass times gravity is going to be our weight. Our combined weight here appears to be 18, or at least our combined mass, anyways, appears to be 1,800 kilograms. So I'm just going to write here that we have a few things. We have the weight, which is negative mg of the elevator cart. We have the force due to friction, which I'll call Fk. And we also have the tension, so we'll call capital T, of the cables provided by the motor. So there's a lot of forces happening here. We basically have 3 forces. And we can find tension. Tension is going against these. And in fact, I don't know if I have space here to write it. Maybe I kind of have a little bit of space. So let me just say F net is of course equal to the sum of all of the forces. And the forces in this case are tension, friction, and weight. And we know what these are. And in fact, notice our friction really is negative, so I'll just write that for good measure. And really what we're going to have here is Let me see. Yeah, I guess we could write it like this. T. I guess that's fine. So we'll have T minus Fk minus mg. So again, the net force is the sum of the forces, which is the tension against the friction and the weight. And the net force actually is 0, which is kind of weird, but it's not too weird. Because notice, F net is what? F net is mass times acceleration. And here's kind of interesting fact. We have a constant velocity. Constant velocity implies that this acceleration is actually 0 because our velocity is not changing. So for that reason, we can actually say that this is indeed 0, which is good. So now we can actually solve for their tension T. Otherwise, we couldn't solve for T, which is kind of why I paused for a moment there. So notice Fk is given to be our 4,000. Mg is given by gravity times our 1,800, which we'll figure out, and then we can solve for tension. In fact, let me just write over here. The tension is going to be Fk plus mg. So that's going to be 4,000 plus 9.8 times the mass. Kind of wrote it in reverse, but that's okay, which is at 1,800. So we'll see what our tension is about, and then that is, notice, that's actually not our net force, but that's basically the force of the motor itself, and we want to find the power that the motor is using. So the force of the motor is just the tensions on the cables, basically. So now let's figure out what this is using our calculator, and notice they cut off a little bit, so let me just, whoops, there we go. Let me just tilt it over here so you can see what I wrote. I just wrote 9.8 times 1,800, and now let's use your calculator to figure out what T is. Okay, so my calculator actually gave me about 21640, it's a pretty large number. 21640, or is it 460? No, yeah, just, and that's of course in newtons. So that's the tension, which is basically the force provided by the motor. And now we can find the power that the motor needs to achieve this tension, basically. And what we're going to do is just consider this formula here. So in fact, just to make this kind of short so I don't have to race too much, let me write it over here. So our power is equal to force times velocity. Our force applied by or supplied by the motor is just the force due to the tension in this case. So I'll write T times the velocity, which is given to be 3 meters per second from the problem. So notice this is just 21640 times 3. And that gives me about, if you round, actually you don't have to round because it's a nice whole number. It gives me 64920. 64920. And we know based on this discussion that that is going to be in watts. 64,000 watts. Again, this is metric, so you can write this as kilowatt. So in fact, this is 64.9 kilowatts. So there we go, we're kind of done. I say kind of, because now we have to convert to horsepower. This isn't too bad because notice 1 horsepower is 3/4 of a kilowatt. I guess we can multiply both sides by 4/3. So we have 4/3 horsepower is equal to 1 kilowatt. So then multiply both sides by this. So long story short, we have to multiply this by 4/3. And I get about 86.6. Yep. About 86.6 horsepower. And this is a good place to stop, and a nice conclusion of energy. It was a long discussion because there's a lot to discuss here. But again, we started with work, we fought our way through kinetic energy and the Work-Energy Theorem, and then we saw some potential energy, gravitational and spring, and then finally power. So I'll see you in the next video. We'll be discussing collision and other concepts involving motion. Basically, we'll be discussing momentum. So momentum is a good application of, well, collision. I guess you could say collision is an application of momentum. But anyways, we'll see when we get there. It's not too bad. Just long story short, it's basically just mass times velocity. But we'll see that in that video, and I'll see you then. Thanks for watching. Hope you enjoyed. See you then.